welcome to the 12th meetup and for joining us here at Daemon. So today we have got a lot of talks and a lot of presenters. So we'll be starting off with a talk about integrating Huggingface chat and the latest Sagemaker features from Damien, who works for Daemon, and also Jenny, who works for AWS. Following on from that, we will take a quick break. Then we will have a presentation from Ben and Jordan at Datasparq on dynamic allocated seat pricing using reinforcement learning. Then we have an exciting talk from Lawrence Knight, who is head of health data science at Vitality, about what you need to know if you think about AGI. And then following on, we'll have a quick lightning talk from DeBurgo, who also works for Daemon, about how he helped make some blog automation with ChatGPT. So first off, I have some words from our head of data, AI, and ML, Ian Ray, about Daemon.
I just got the link, right, so I just didn't realise that you was talking later. Thank you. Thank you. Got that. Thank you for coming, everyone, and we're really pleased to host everyone here. I've spoken in the past, and I'm sure many of you have been to our previous events. I think for us at Daemon, it's really important that we get everyone together and we speak really transparently about what's happening in the industry. It feels like it's a really great opportunity for us just to come together and really share what everyone is up to. I'll give you a bit of quick blurb on the company, if I can. So, I won't go into all this, but we're a nice company. We've won a few awards, which is really nice for our well-being, for our culture, and for our tech as well. We're about 150 permies strong. We're obviously based in the UK. We also have an arm in South Africa as well, so we're quite diverse. We run with about 25% of our base with trusted partners, so contractors. We have loads of different clients, so won't go into them all, but we work for small startups, we work for big FTSE 100 companies. A couple up here that we're going to talk about today, actually, and Damien and Jenny are going to talk about Conjecture, so one of our startups that we're working with. But you can see the idea of this slide is we work with quite a wide range of diverse clients. Got to mention this, otherwise our marketing department will not be happy with me. So we've just pushed out and undertaken a survey with 150 big corporates just to get their understanding, their belief and their direction around where they see AI going for them, their kind of investment, what they're going to be doing with it, their kind of timescales. Actually pulled together an ebook. This is our website. It's on there. It's got my name against it. Very proud. Please go and have a read if you're that interested. And then lastly, we are a very busy, growing business. Check out our openings. So we're looking for people with skill sets, all different kinds, some examples up there as well. But please hit the QR code just to find out a little bit more. That's it from me. Welcome. Thank you for coming. Great to see you all, and please enjoy.
So first up, we have Damien and Jenny with the talk on Huggingface and Sagemaker, and a very long title.
Right. Hi, I'm Damien. I'm also from the same company as Ian and Noman Daemon, hence the branding. So we, as Ian might have mentioned, we work a lot with enterprises, but we've also started to work with startups a lot recently. And there's a bunch of stuff that we've learned that I want to basically share with you guys about how to do hosting of large language models fairly efficiently. It's in the context of this product of AWS called Sagemaker, and we have an AWS expert, famous person, Jenny here. She really is. She knows her stuff when it comes to AWS and Sagemaker. So I'm really happy to have been to be able to collaborate with her, and we collaborated on a bunch of projects as well. So this is sort of the accumulation of a bunch of learnings that we've got after working with some various different startups and so forth. But there is one startup in particular that I want to highlight because they were, for me, one of the first people that I let's skip on that. One of the first set of startups that joined us on this journey, right, of developing our machine learning and artificial intelligence practice, whilst they also developed their product. So there are, the name is Conjecture. Nobody here from Conjecture here, I think, right now. But I did want to shout out to them and give you a bit of a demo. Before I do that, let me just quickly talk about the rest of the talk. So you've got a bit of context as we go through. So I'm going to talk about the use cases of chat, voice chat, large language models in general, right, to set the scene for why you might want to do this kind of thing. And then we're going to talk about hosting inference, right? So inference is when you have already trained a model and you want to host it to use it in your application. So think OpenAI chat, and we'll give you a demo from Conjecture because I wanted to showcase some of their stuff. And then we'll talk about, okay, how would we do that in AWS? Like say you wanted to build a chat application. How would you do the machine learning hosting part with an AWS? And then basically the rest of the talk is about that and how to do it well, including, and the part that Jenny will talk about, because she's just come fresh from reInvent, which is the AWS big conference, with some of the latest features from Sagemaker, the flagship machine learning product of AWS. And she'll be talking about how you can use that to keep your costs down and keep things efficient. And then at the end, I will talk about how we could incorporate Huggingface TGI, text generation interface, into this set of solutions. The reason I want to talk about that is because it makes a bunch of stuff easy, right? It's some of the best practices all wrapped up into a container that you can deploy into any cloud, but in particular, they make it easy because they're partnered with AWS. They make it easy to deploy into AWS. I don't mind if people stop us for questions along the way. So if there's any point that I've forgotten, particularly those of you who care about me, stop me, and I will try and answer them. Okay, so I was talking about use cases, and in particular, I wanted to talk about the use cases that this startup has been working on, the startup Conjecture. They are creating a bunch of different products. So one of these products is this Axiom. Thank you, Jenny. Apologize. We've got remote listeners who didn't hear that demo. Apologies to you guys. Basically, what we saw was, and this is for our remote listeners, we saw a voice chat, a real-time voice chat. So that's the kind of thing that you can do with this technology, right? So I wanted to set the scene. Okay, we've got various different machine learning models working in here. We've got text-to-speech, speech-to-text, and a large language model in there as well, underline this chat. I wanted to also acknowledge, thank you, a couple of other products that Conjecture are coming up with. Cubed, which basically turns your workflow tickets in something like Jira. The AI looks at it, looks at your code repository, goes through your code repository and comes up with some suggestions about how to implement that ticket. So it's quite a cool little feature. And they've got this thing called Hypercube, which is works inside your IDE and helps to convert those tickets into actual code and work in there with the chat interface as well. So I wanted to share those with you to acknowledge that Conjecture has been, with us in this very early parts of the stage. And you can do lots of other things with language models. You guys all know pretty well, so I'm not going to dwell on this slide very much. But this is just to set the scene for the sorts of stuff that we're going to talk to you about now. So you're building an application. You've got, you might have your web stuff, you might have your database, et cetera, et cetera. But at the heart of machine learning, artificial intelligence driven application is the machine learning model itself, whether it be text-to-speech, speech-to-text. In order to use that, you need to host it, right? You need to have a server somewhere where that model is running. You can access that server, make requests, bring those requests back to your application. Now, I wanted to talk about in particular how we do it, because this is what we have been doing. We've been working with the startups who have been working with the AWS startups program. So that's what we've been doing. We've been doing it in AWS and SageMaker. So when you want to, so I'm going to talk about how you'd normally do this, how you'd normally host a model. You'd use something a bit like this. So you've got your model, but your model is just like a neural network. By itself, it's just numbers. You need to be able to run it. So that's what your inference code is. So this is Python usually nowadays, but it could be whatever inference code. But that's all very well. You can run that on your laptop, but you want to run it repeatably, reliably, scalably in the cloud. So you're going to wrap it in a container, a Docker container, more or less usually. And that will allow you to deploy it repeatably to different services. I'm going to talk about some services that you can deploy it in soon, and you'll deploy it on some sort of computer. Well, you could deploy it on a cloud server, or you could deploy it on something that is a managed service that takes your container and runs it for you. And then once you've got that up and running, and you will need some network infrastructure there as well in order to get the HTTP requests routed, you'll make invocation calls. Your application will ask, okay, here's some text input, give me some text output. The model itself, well, you'll need to pull the artifacts from somewhere. It's not something I'm going to go into. And I wanted to acknowledge that AWS is one of the main cloud providers. They're the biggest cloud provider in the world. Are they still?
I think so.
Okay.
I have to say.
They offer all these things. Most of the main cloud providers do. But I guess this makes it better than hosting it on your laptop. The network infrastructure, right? They've got data centers all over the world. Okay, so let's say I've made the decision. It's there's a lot to go into this kind of decision, but let's say I've made this decision to host on AWS. I've got some options, right? So I could host my container or my code on EC2, that's a virtual server. It's a bit hard because I have to do a bunch of stuff myself. It's basically a computer in the cloud. I'm going to run my code on that computer. Okay, now there's a problem of orchestration then. Okay, so I want to run this, but I want to run in a way that's scalable. I'm going to have my containers. I want to be able to increase the number of containers. I want to be able to route things to those containers in a good way. Well, one of the main solutions for that is Kubernetes. So AWS offers a managed Kubernetes system. Now, in the work that I did, I found that a little bit complex to set up because I'm a little bit dumb. So I moved on to this slightly more AWS native option called ECS, which is an easy container orchestration system. It's called short for Elastic Container Service.
Yep.
Yeah, and you can use this with EC2 instances. So EC2 instances is basically the name for all the arbitrary kind of instances, cloud servers that you can use with AWS. And lots of them have GPUs. Lots of them have really big GPUs as well. So we're talking 80 gigabyte A100s, H100s as well, going down to the old ones as well. So you get these powerful EC2 instances while the ability to orchestrate them, do load balancing, so those requests coming into the instances are balanced across those instances. And then there's this option, which is a fully managed one, right? So this is Sagemaker has a lot of options, so a lot of tools, a lot of services. But when it comes to inference, that is hosting your models, it gives you a fully managed system there as well. It can contain all this extra stuff, but API driven. So you don't have to worry as much about configuring the containers and doing everything for yourself. You just call some APIs and run it. So that's the one that we've been working with most recently, and that's the one that I want to talk about. There are times when you'll want to use this, and times when you'll want to use this, times you'll want to use this. I might suggest that if you're doing stuff at the cutting edge and keep doing weird stuff, then you might want to do this. But for most people, something like this will make things a lot easier, and it still can host arbitrary code, arbitrary containers. It's not so managed that your hands are tied. So what I'm going to do, I'm going to hand it over to Jeannie now, because she knows all about this stuff in a lot of detail, and she's going to talk about some of the latest features that will enable you to use Sagemaker in the best way that you can, efficient, cost saving, and everything. Thank you very much. I'll join again soon.
So, quick question: cost-wise, ECS or Sagemaker?
Yeah, we're talking. Jeannie, you could probably answer that one, right?
Yes. So it really depends on, in terms of cost, which one is better. So there is no best service. It really depends, because you can deploy you can get more management overload with ECS, and with SageMaker you can just deploy in one instance, and it will allocate. We will see in a moment. It will allocate the models in just one instance with many GPUs, while you have to do this manually and maybe without succeed in ECS. So it really depends on the number of instances. Of course, there is the pricing is different for SageMaker because you are not basically hiring someone to manage the infrastructure. You can, as machine learning engineer or even as an experienced software engineer, deploy a model in SageMaker, but that's basically the pricing difference. Okay. Okay, so we will talk about real-time inference, just because we want to use large models in an inference way. ChatGPT, for example, is real time. So when we talk about Sagemaker, there are different ways to use Sagemaker. From the bottom, we can have custom containers where you can bring your own code, basically, your own container, but you can also get optimized containers, deep speed, accelerated from Huggingface. Any open source NVIDIA package will be or is already available in Sagemaker. And there are also options to manage some frameworks like XGBoost, PyTorch, TensorFlow, MXNet. Most of the open source frameworks are supported by Sagemaker, so you don't have to implement from zero, or you don't have to build your own container if you are using one of those frameworks. And you have the option to use algorithms on. So we can use all of these options in a real-time fashion through endpoints, single endpoints. That means in a single instance. We can use multi-container endpoints. That means we can deploy multiple containers per instance. We can use multi-model endpoints. That means we can host different models in just one container. And this is actually something we want to do if we want to reduce cost. And we have this serverless option for real time, but we are going to skip this part because it does not support GPUs. And specifically for large models, we need GPUs. So today we will focus on single endpoints at the beginning, and then we will talk about multi-model endpoints for large models. So let's say we have a fine-tune or even just a simple Llama model, Llama 2 13 billion models, and we want to put this in production. So we can just download the weights from Huggingface directly, or we can have our own weights fine-tuned. So the first task is to start calculating the amount of memory that we are going to need. So again, we are choosing 13 billion parameters for this model. And if we are using FP32, that means 4 bytes, the model itself will have 52 gigabytes. Okay, but there are more considerations for this model. So in the coding process, we will have input tokens that will produce their attention key values, tensors basically, and these tensors are kept in the accelerator memory. So this will increase from between 4 and 10 gigabytes, depending on the size of the model. This is basically referred to KVH. And this is something that we need to consider, and also some overload, let's say for the input-output tokens, and imagine these 2-3 gigabytes. So we are calculating roughly 65 gigabytes of just to host this model. So let's use Sagemaker to deploy this model. Okay, so again, we will have the model, and we have been using with Sagemaker LMI containers. So these large model inference containers come with packages already installed for you, Accelerate, Huggingface, PyTorch, the latest version of the frameworks. So you don't have to create a Docker image by your own. And you can get some quantization and attention algorithms in those containers. And remember, you will deploy this model in an instance. As we saw before, the size of the model is 65. So a P4 instance in AWS means this might be an 140 gigabytes or a 180 gigabytes, right? So if we want to scale this, then we might need to use another instance, because maybe imagine you having a chat application and you get more requests, then you have to spin up a new instance. And this will, even if you're not using entirely the instance, because imagine you're using an 800 instance in Sagemaker, there are 15 gigabytes still without being used. So this is our request, and we will return a response in a string. Okay, so we have hosted in a 1P4DE instance this model. But then you realize, I want to put on top of this model, or I want to increase the number of endpoints, and I want to add some guardrails. I want to create a toxicity endpoint, basically an endpoint to detect PII information. And also I want to add embeddings, because I want to use a knowledge base. And then I want to go multilingual, or I want to do text classification, and so on. So I will have many LLMs for different tasks with different purposes and different models, and it will increase the operational overload basically for my machine learning deployment. So how can we pack all the models in one endpoint? That's possible with multimodal endpoints. So we can combine many models in one endpoint and call them through the same basically URL. Okay. So what are the benefits of using multimodal endpoints? So we can be cost efficient because we don't be spinning up more instances. We will spin up a big instance and we'll put all the models inside one. So it can scale to thousands of smaller models again. Already we have a dynamic model loading with SageMaker multimodal endpoints. But there are some trade-offs we have to consider. For example, the cold start. This is basically adding latency every time we add a new we add a new model, or every time we are not requesting or sending requests to a certain model. Okay, so imagine you have two models, you're sending 100% of your traffic to the text generation model, but then you want to add a new model, imagine a Stable Diffusion, and then you have to wait a bit until the model loads in the memory. So it's good if you have small models. It will add some latency. And for our use case, for the model we want to deploy, doesn't work. So what do we want to get from SageMaker? How these hosting foundation models works in SageMaker? How can we make this cost effective? So we want a solution that can pack multiple foundation models, not only the small one, but also the big one, that can combine small and large models in one place. We want to dynamic load in the model based on the traffic. We want a solution that can help us to set up and allocate resources like the accelerators. We want some, again, this one, we want to scale based on each model, based on the request of each model and the resources for most of them. And we want to also store the metrics. We want something that can allow us to check if we are getting more requests from one model, or the capacity for that instance is not available anymore. So what are the new features that have been recently added? Not recently added, but just released last week. We tested these features since August, and we have been working with the SageMaker team to make this happen. So we test internally our services based on what customer ask. This one of the features that customers were asking, like, how can I cannot do dynamic allocation. I cannot hire people that can manage the GPU. Can you do this for me? Basically, that's what the service team does. So now you can deploy hundreds of models, reducing the cost because you don't have to spin up one entire instance and underutilize resources. You can auto-scale, you can create new policies in SageMaker per model. Before it was per instance. So even if you are not using the entire instance, it will scale because the auto-scaling policies were based on the instance, the hardware itself. You can dedicate resources, hardware resources per model. So it has been customized per model. There is a new feature called Smart Routing that achieves 20% of lower latency. And we are adding compatibility to more containers. So everything that comes with Huggingface or Huggingface has released, they make sure it's compatible with SageMaker. So this is a new model abstraction. Let's say new because the component that has been added is basically this scaling policy. So before with SageMaker, we already had these 4 components. To create an inference implementation, an inference component, we had before to define the container URI. Basically, if you want to create a SageMaker endpoint, you had to specify a Docker image. And this image needs to be stored in ECR. Imagine ECR as Docker Hub. Then you need to specify where the model is located. That's the model stored in S3. Then the hardware requirements, how many GPUs you need, CPU cores, if you're using accelerators like inferential training, you need to specify the number of neuron devices and the minimum and maximum memory, and how many copies of this model do you want to host. Now, you need to specify this scaling policy. So you can now create rules per model, and you can get the metrics from this per model in CloudWatch metrics and CloudWatch logs. So deploying inference components, again, what we have just seen now, requires 3 steps. So you need to pick first the instance, the hardware you will be using to create the Sagemaker endpoint configuration. And then you create the Sagemaker endpoint, and you will deploy using the characteristics or the features you just defined. So something I want to highlight here is the auto-scaling part, because this is the feature that has allowed conjecture to scale their architecture, their LLM deployment. So imagine you are building a comic application, comic books. So basically, to create a comic book, you need to have something that creates those images, a stable diffusion, and an LLM. So let's say we're using a stable diffusion and Llama for this purpose. So I have one A10G GPU. Okay, it's not a P instance, it's a G instance. And what I want to do is, again, we need to define now the scaling policy. So my policy says the minimum copy I need to have in this instance is 1, and I will scale up to 4. That's the max copy. The scaling policy is based on traffic, but you can configure this to scale based on, let's say, on the weekends you want to scale, so you can configure this scaling policies. Those scaling policies now are very similar to the EC2 ones. Okay.
So, the endpoints for the light eye controls, does it support model variants and even testing of that configuration?
Yeah, those configurations, the same configurations remain for Sagemaker. So we just added a new attribute. Yeah, this is scaling policy one, but the old one remains.
And so does it matter the state as well? Because like you have 2 instances, and by state I mean your past conversation, because that's important. When you have servers, it's important to manage your state. So is that on automatic? Because if I'm in a conversation, for example, I want all the future conversations to go to the same instance because of my past history. But probably this is like taken care of automatically, right?
So that keeps with the session. That means that comes with the session you open with this inference endpoint. So if you open a session in this endpoint, in the Sagemaker endpoint, then you are having the communication unless the session is closed. But this endpoint will be hosted in one instance. So when you spin up a new instance, and then you are creating a new session, a new request, this new request might come or might go directly to a different instance, depends on the overload of this instance or not. So you want to deploy one model first, a small one. Let's say Stable Diffusion is smaller than Llama, so you can deploy a Stable Diffusion in 1 GPU and Llama, let's say, in 2 GPUs. And you create a new or a different policy for this. You can scale again based on traffic. You might set up, I need just minimum 1 copy of this model and max 2, 4, or 3. So that works for this instance because it has GPUs. What happens with, when the traffic increases or changes? So if we increase the traffic for this Llama model, we cannot allocate Llama 2 model here in this instance, right? Because it takes 2 GPUs. So what this auto-scaling policy will do is create another instance. So it will allocate 2 copies of the model, right? Because my auto-scaling policy says max 4 copies, so I'm adding 2 to utilize the compute resources. What happens if the demand for this model increases? Instead of spinning up a new instance, it will look for the resources that are idle. So in this case, the first instance has still space for this Stable Diffusion model. So it will allocate resources there. So the number of instances will scale up to accommodate these inference components. What happens if now that is nothing has changed and suddenly I'm not using anymore the Llama 2 model? And again, the outscaling policies start working. So it will reduce one of these instances, one of these models, because it's not using anymore. And if we increase the request for the Stable Diffusion model, then it will add more copies where there is a space for it. So instead of creating another instance, it will use the resources that are not being utilized to optimize the cost. If we are not using anymore the Stable Diffusion model, then we can scale down to 0. That means we can scale down to 0 the model. We can get rid of the model for complete, but the instance is still there. So just be aware that when we say down scale to 0, the model means we cannot get the model anymore in those instances, but the instance is still alive. Okay, and so SageMaker will consolidate the models in the future. It's a feature coming. So once we don't have any more those Stable Diffusion models, I have resources idle here. So I can just easily move from one instance to another. That's a feature that is coming with SageMaker. Okay, so this is the feature that we are using with Conjecture, basically, to scale based on demand. There is a new another feature that was released in September. And you probably have seen this before: the streaming responses from the endpoints. So you don't have to wait until the entire response has been generated by the model, but you can instead receive tokens as the model is generating them. So this part is this has been released already, but we are still using this for Conjecture. And with these features, we have Daemon and AWS has designed this architecture to be utilized.
Thanks. I like those animations. They're really cool. Hi, everybody. Yeah, so with those inference components and with the SageMaker hosting inference, we can build out applications. By the way, we should talk about the whole session-based stuff, because most of the time your state will be in the using application. So unless you're doing very special purpose stuff, let's say we've got an application. It could be a chat application. It could be the comic book application or something like that. But any application where you need real-time inference, real-time responses to users. This is one possible architecture for that. With this architecture, we've got basically the models hosted on SageMaker, and we've got the application itself hosted on ECS. Remember I mentioned ECS before. ECS is
Elastic Container Service.
Elastic Container Service. It's not as easy as SageMaker, but it's not machine learning focused. It's generic containerization and orchestration tool like Kubernetes, but simpler and AWS native. And with ECS, we have two options. We can either orchestrate instances, EC2 instances, or we can figure that there is even a machine here, and we can just orchestrate containers directly, and that's called Fargate in AWS. So normally, unless you're doing very special purpose stuff like with GPUs or something, this is good enough. So what we do, and when we create our applications, we use ECS to host our backend of our application. There, maybe that's running Golang or Node.js or Python or Java or something like that. You'll host it on there, and it gives you the ability to scale horizontally, as much as you want, because it's an orchestration service. We'll add in more tasks as the traffic grows. You can scale it according to different kinds of metrics, and it comes with support for load balancers, so ways of balancing the traffic coming into those instances, HTTP requests usually, into those different instances. And you can see here that we've got these things called subnets and availability zones. So this is the sort of thing when you get into the cloud, that you use to keep your work private, to basically control how the information flows between the different parts of your solution. It's the networking. It's the networking aspect here. And what we are doing here is we're dividing your application across different availability zones. These are basically different data centers, so that you've got that resilience. That if one data center goes down, you've still got tasks running in another data center. But they're still, as far as the ECS application is concerned, logically one thing. So you don't have to worry too much about that. You specify, okay, I want these tasks to be distributed across 2 data centers, and then try to forget about that unless it becomes a big problem. In this example, what I haven't done is distributed them across different regions, right? So that takes a bit more manual effort, but this stuff comes right out of the box. So I've got my application running here, and I've got, in this particular case, it's more like the application that you saw first. We've got a real-time speech chat kind of a thing, because we've got 3 different models. We've got a chat model, a speech-to-text, and a text-to-speech. And you can see that we're hosting these different models within potentially one or more of the same kind of same instance, right? So all of what Jenny talked about, right, the packing of different models into instances in order to save costs and make things more efficient, we're doing here. So we've basically generated one Sagemaker endpoint, because we want to host all this stuff on something like this instance, which contains and by the way, this is where these inference components come in useful, because I've got to come over here so these guys can hear me too, because you might have an instance with 8 40 gigabyte, 80 gigabyte GPUs. Those things are expensive, right? You don't really want to waste that hosting, maybe your model needs 80 gigabytes, but there's, it means you need at least one of those things. You want to pack those models on here. So yeah, and then you've got the application auto scaling. So this is the application auto scaling can be applied to your application. And as Dean mentioned, there's actually 2 layers of auto scaling with these inference components. There's auto scaling for the instances themselves and for the inference components, right? So so it's useful. I had some notes that I wanted to mention as well. While I was listening to Jenny, I came up with some ideas. Right, so the good thing about this auto scaling, right, is that once you've got an instance up, you can add models to it and take models away. What it doesn't do out of the box is scale to 0. So if there's nothing working, you've still got at least one instance up there. And the most expensive ones can cost you upwards of $30 an hour just to keep it up there, right? So the problem with and that's basically the only problem left from my view. I like this solution because it allows you to abstract your machine learning models as containers, right? You want to containerize everything. You want to keep everything separate from each other. It's a great abstraction. If you started trying to host your different models within one container, it starts to get a little more difficult. So we have a solution for the scaling to 0 problem, but it's built on top of inference components, not with inference components. And basically, the way that we do that is we use some kind of orchestration in order to understand when the container is not being used, when the model's not being used. And we're using CloudWatch metrics. So Jenny mentioned CloudWatch metrics as the way that they do auto-scaling, because basically the auto-scaling component watches the number of indications, or you could also use the amount of GPU usage or the memory usage or and so forth. In order to understand the state of the instance. We could also use more cloud-native stuff like Lambda functions and so forth, CloudWatch alarms, but we chose to use the application itself to orchestrate that, and that's sitting in ECS. Remember I talked about ECS as where we host our application? So then once you scale the container to 0, when do you want to scale it up to 0? Well, when it gets used. So if somebody attempts to invoke the model, if you need to invoke the model, what you're going to do is you're just going to attempt to invoke it. And then if it's not, by the way, I didn't say why scaling to 0 is a little bit harder than normal auto-scaling. The reason the scaling to 0 is a little bit harder than normal auto-scaling is because you can collect metrics of running containers, but you can't collect metrics of containers that are not running.
Nothing
right, so if they've gone to 0, you can't count the number of invocations as 0. So that's why you have to do special purpose stuff like this. It is possible to build it into your high-level tool as well, but usually people have special requirements. And it's a little bit niche to do this, actually, because once you get to scale, it's not going to matter as much. you're going to need at least one instance, maybe 50. I don't know. So this is the sort of thing that you will use when you're starting to prototype and pick up things, and maybe you've built a product and hasn't quite got traction. So this is the sort of thing you'll use at the start of your iteration. Once you've moved on, this stuff will become less important, but you do want to use it for the next project. Did you have a question?
Yeah. If you're starting from scratch and you're trying to scale and you're doing all this stuff to scale to zero, why is there a reason to consider Amazon Bedrock instead, where you're just taking the inputs as you use it on the actual?
Yeah, I mean, with Amazon Bedrock, you know, you've got a menu of models to choose from, and you don't have the cold start problem because they're already up there for you. You just have an API. It's great. But what if you want to use a model that's not in Amazon Bedrock?
Yeah, I get that.
Or you want to train your...
Yeah, so that's why I'm asking the question. The fact that at what point do you take a cutoff of saying, okay, fine, the response is coming from like a large language model, coming from Anthropic or Cohere, whatever, isn't good enough for me. I want to move to another.
Yeah, I think that's just it. I mean, Amazon Bedrock, by the way, is like a really managed version of this sort of stuff. It's an API, right? You can hit your API, you can say, okay, give me some chat stuff. This is for everybody else's benefit. By the way, the question for you guys was, why am I not, well, when do I decide when to use Bedrock and when do I decide to use something like this? Yeah, I think basically I would normally try something like Bedrock first because it's more straightforward, it's managed. Okay, for some scenarios, it might end up being more expensive. So if you've got the resources, you might want to consider moving to something like this. Eventually, you're an enterprise or something like that. But yeah, I would almost always try something like Bedrock first. And then when it's not good enough, maybe it doesn't have the right model, maybe its performance isn't good enough and you have to do custom stuff, then I'll consider moving to something like that. So it so happens that you know, we've been working with stuff that has a bit of custom requirements so far. Do we have time to have a couple of questions during this?
Yeah, you still got another 2 minutes.
Okay. Somebody at the back there had a...
It was just one reason you might want to host your own model would be around the protection of personal information.
True.
So I think that's one of the reasons most models into.
What do you reckon, Jenny? That's...
For PII?
Yeah.
Even with Bedrock, all the information that you share with Bedrock is not shared with AWS or any model provider.
They don't train it, and
No.
legal teams will allow you to use it as long as they have that.
Yeah. The conjecture, they build their own model basically. So it's not a fine-tuned model. They build from scratch. Just to mention who this startup is. So the founders are creators of Eleuther AI basically. So they built GPT-3. So they built their own model. So that's the reason why they didn't go for Bedrock or any managed service. So they decided to go because they also were building a different approach for this model. So it's not, so they are focusing AI safety. So the model is basically is a different approach for this. So that's why they hosted their own model.
That's addressed your thought there? It was you that asked that, right?
Yeah, I mean, I wouldn't advocate for hosting your own model actually. But I've got experience of kind of risk teams in large organizations that are very reluctant to allow you to send this information to third parties, no matter what guarantees they provide. I think that's easy in my experience, but that certainly was the case some months ago. So
yeah.
Even if you host your own model, then that means you're processing tons of personalized PII information, and also you can pay like 1P4D. So that means that you have a lot of money as an enterprise, because those instances cost a lot, especially if you're managing different endpoints and models. It makes sense. But the main reason why this startup, they use P4D because it's not common for a startup. They want to use managed services or APIs, right? Because they are just growing. So they did this because they have a different model that wanted to host.
I should say that latency might be important to you as well.
Yeah.
If you need latency, then, well, I don't know. You can almost always do better with your own.
With Bedrock, you get this, but provision throughput for a startup is like the salary of the entire team. So they won't be able to use provision throughput. For an enterprise makes total sense, depending on the number of requests, but for a startup makes no sense to use provision throughput. You can fine-tune models as well in Bedrock, but not this model and not all the models in Bedrock. At the moment, only Llama and Titan models are fine-tunable. Coming Anthropic, you can fine-tune Anthropic in the next year, but for this particular model, it was a bit different story. You have a question?
So if you take two different cases, you have the edge case and the pipeline inference case. So edge case will obviously be very sensitive to latency, and pipeline case may not be sensitive to latency. In those two cases, where do you put the orchestration versus the Lambda functions, the cloud functions? For inference.
Are we talking about the autoscaling stuff or just in general?
I'm talking about
Right.
and in general, like it applies in both scenarios.
So when you're talking about edge, you're talking about edge computing, things like
So
where
edge,
you
edge cases when the model is customer facing.
okay.
Case is edge case basically. Otherwise, it's pipeline case where the inference is part of your pipeline and it's not very.
We're not even talking about that one here at the moment. I'm talking about the real-time inference stuff.
And like if you just take orchestration application and which one would you?
Well, so if I'm using Sagemaker, I might not even have to care about this because I could use batch processing to do it, which would spin stuff up for you. I wouldn't even do any orchestration at all. So the question was for these guys, if my workload was more backroom and I didn't need fast latency or anything like that, what would I do for the orchestration? I don't think I'd even have to build that if I can use Sagemaker's batch processing or something like that. Anyway, let's move on so we can get through to the end of this. So yeah, let's get on to the next one. So actually, I'm going to have to go through this very fast, but I wanted to talk about how within this context of hosting models, we can get a bunch of out-of-the-box stuff, right? So you don't have to build your own stuff in order to make use of all of this infrastructure. You can get really fast, low latency chat models and so forth using the Huggingface TGI, text generation interface serving container. So Huggingface has a partnership with AWS, so it makes it very easy to deploy their stuff onto SageMaker stuff. But if you don't know about Huggingface, they're responsible for some of the not quite seminal, but some of the most important open source stuff around large language models, the Transformers library, Datasparq Accelerate for doing distributed training, reinforcement learning, and so forth. I've got this thing called the Huggingface Hub, which contains a bunch of data sets, models. You can find all different kinds of models on there. So they host all of these things, and they have a bunch of chat models as well. Thank you. So you can use it. Can we skip through a little bit? So we can use it to, if we go to Huggingface Hub and we find a model, like for example, Llama 270B, we can easily find instructions for how to train that with just a little bit of code do some fine tuning with just a little bit of code on SageMaker and inference. So you can go into there and you can find some code. Can we skip? Yep. Some code for deployment. So this is the code basically that you would need for deploying. I think this is pre-inference components actually, but you can use some code a little bit like this for deploying this onto SageMaker. Right. So what is TGI? Right. So let's say you don't have the money to make your own high performance chat engine or inference engine or whatever. It's an API and also a containerized solution. So remember we were talking about hosting containers for doing very efficient performance inference hosting of large language models. So we've got the ability to do tensor parallelism, which means you can use bigger models than you might not normally be able to host on a single GPU. You can shrink those models if you want dynamically. All these are for increasing throughput and decreasing latency. And if it doesn't work, if your model hasn't been optimized for using here, you can still host it with this. But this is different from the reason why I wanted to talk about this one is because this is a little bit different from the sort of main out-of-the-box ways of hosting these models. This is performative, right? It has all the latest tricks. And so, and it's got streaming as well, right? So it's got all the tricks. If I just wanted to get some of the latest stuff, not all the latest stuff, but some of the latest stuff out of the box, I'll use this. And you can see here that there's a bunch of models that I can get out of the box. So as long as it's been pre-prepared for this. So Mistral is a relatively recent one. The Llama is there, Falcon is there, Starcoder is there. Can we skip on to the next one? So what we what we did is we incorporate that into it's a bit of code, isn't it? I had to show some code. I had to do one slide with some code. But this isn't really code. This is just the information that you would need to provide any application that you build in order to decide what the new model is that you'll deploy. I want to switch between Mistral or Llama. I want to switch to StarCode. As long as one of these models are here or is on the Huggingface hub, I can deploy it. And I just give information about this image. This is a pre-built Docker image that contains this text generation interface. So I've got the container, actually. I just need to tell the container which model I want to deploy. So I told it I want to deploy this model here, it's Llama 2 13B. I want to deploy on this instance. When you're using inference components, you also want to tell it, by the way, in order to do this, in order to do something like this, you need to do a bit of custom build, right? But this is the level at which you will come to, which you can quite, easily swap out once you've built that thing for new models. Specify how many GPUs you need and give it some information about how you use it in text in a chat engine. So this is interesting as well because you can basically I wanted to show that with Sagemaker inference and Huggingface TGI, you can very quickly get to a self-hosted, very performant chat. Let's move on to the end. So it's been a joy for me working with this stuff. Just in the last 6 months in particular, picked up all this stuff, and I just wanted to share with you guys today some of the cool stuff that I learned. Because this is the kind of thing that we want to do in this community, and hopefully show off myself a little bit as well. And yeah, I also wanted to share my partnership with our AWS colleagues. So thank you very much for listening today.
Great. So welcome back, and I hope you all had lovely chats. It was really hard getting you back in your seat, so I think you did. But I'm excited to introduce Ben and Jordan from Datasparq with their presentation on dynamic pricing of constrained airline ancillaries using reinforcement learning.
Cool. We'll explain what an ancillary is. Yeah, thanks everyone. So me and Jordan are data scientists working for a company called Datasparq. We build data products for companies with a bit of a focus on route optimization and revenue management generally, but as you can see here, we do a ton of other things as well. What we'll be talking to you about today is dynamic pricing, so that falls under revenue management for an airline. So by ancillaries, I mean all the things that you can buy when you book a flight that aren't the ticket. So the airlines generally try to upsell you onto other products, one of those being specific seats. So we'll do an introduction to what seat pricing is. We'll do a very high level introduction to reinforcement learning, and then talk you through how we set up the model that we've used to solve this problem, go through some results and have time for some questions at the end. But feel free to stop us at any point if you've got any questions. I'll hand over to Jordan.
Do you want me to skip as well? Yeah. Okay, yeah, I'm doing the easy bit. Introduction to seat pricing. Hopefully you've been on holiday before, otherwise your companies need to give you some holiday. But when you get onto most airline websites, you'll see a bunch of flights. You'll probably search London to Barcelona, something like that. Should be quite trivial. You pick a flight, so you've sort of said, okay, here's a flight with a certain price. I'm quite happy with that ticket price, so you've clicked on it. And then usually, like Ben was saying, airlines will try and sell you a bunch of other stuff as well. What's quite unique about ancillaries is that we know something about you by that point because you've clicked on a ticket price. You've clicked on a price that's £200. We know, it's £200 instead of £50. So it kind of helps us decide on what sort of pricing for ancillaries. So it's quite unique in that sense. We already know something about the customer. So from a data scientist point of view, that's quite nice. And obviously, you move on to your booking and you pay money to the airline. So yeah, the focus today is on this part, the ancillaries part. We do actually, for this airline, we do actually price bags as well. But for this talk, we're talking about the seats. And we'll show you what that looks like. You might be able to guess the airline from some of these diagrams. We'll see. It's a big orange one, big orange airline. So this particular airline likes to think about their seating in two categories, premium and standard seating.
Premium being, you know, I want to sit on the front row. Front row, you get extra leg room. You usually get off the plane quicker. So business people love that. Obviously, the most expensive one. Band 2 is up front, so it's close to the front of the airplane. I don't care where I sit on an airplane, but people tend to care from the data. Band 5 is those nice extra legroom ones across the wing. You're not allowed your bag under your seat, which is annoying, but you know, those extra legroom is really nice for longer flights. And then standard seating is just the regular bog standard seating that most of you will probably have been on before. So here's my schematic of the plane. Hopefully you recognize it without the wings sideways. So this airline will price their bands. So these are all kind of like in bands. You don't price each individual seat. It gets a bit unwieldy if you start doing that. But they price their bands in a sort of price hierarchy. Band 1 is more expensive than band 2, etc. Band 4 being the cheapest. Hopefully this makes logical sense that band 1 is only 6 seats and it's high demand. It will always sell out. People want this. So why price it cheaper than band 4, for example, which has many seats and pretty rarely sells out. So that's kind of the situation we're in and what we were faced with at the start of this project. And the goal really is, how do we optimally price each seat band while kind of maintaining this hierarchy that the business want us to maintain. We're not saying whether that's good or bad, but you know, if you work with clients, they will say, you know, this is how we want to do it, and you just do it. You optimize around obviously their constraints. So we have 5 products here essentially. We've got band 1 to 5. We want to know what the optimal price combination is. Obviously, if you see band 2 is £20, but band 1 is only £2 more, you know, each one of these prices have a relationship between each other. So when you're a customer looking at buying a seat, you might just say, well, standard seat is £5, but the premium seat is £10. I'm willing to spend that extra £5. So, you know, you've learned something good about that price combination. Okay, so a little bit about the flight selling period. It's quite important to know sort of the life cycle of a flight. So usually about a year before the flight departs, it goes on sale. And any time in the selling period, you can buy a ticket and you can buy your ancillaries as well. At 30 days to go, so at 30 days before departure, you'll be asked to, well, you're allowed to check in from that time. And when you check in, you'll be automatically given a seat on the plane. So that auto allocation happens by trying to distribute people around the plane so that the plane isn't weighted funny. You might have had that if a flight was delayed. You might have seen everyone reshuffled because a few people didn't turn up, and that happens. So yeah, the problem with that is by that point, if you're automatically assigned a seat, if the weight is distributed funny, you could be automatically assigned a premium seat, which is obviously lost revenue for the airline. Great for the customer, right? So, you know, there's a little bit of playing a game here, trying to sell your premium seats quickly, sell them out so that, you know, the weight distribution will try to prioritize other seats. So this is a bit of a black box but this auto allocation thing was a bit of a black box, and we don't really have access to the middle of it, but we're playing against it, essentially. That's what the problem is. Okay, so a little bit on how they price now, or actually how they priced before we came in. Very manual. This is quite standard with a lot of trading teams. They look at a dashboard, look at some metrics, and they're like, oh, there's a little jump. I'm going to react to that. I'm going to set this price to this. So usually there's a bit of a manual process, a rule-based approach, which is fine. Usually it works quite well. The problem with this particular trading team, they hadn't actually adjusted their price to the standard seating. They just set, I think it was like $4.99, something like that, all the time. So, you know, there's some lost revenue there. They could set $3.99 and make, you know, sell more. You know, who knows? There might be a price sensitivity there of their customers that they're missing out on. Yeah, and previous to us, there was a data science team, internal data science team that attempted this with just traditional ML methods, but there was quite low volume of data in their premium seat band, so they couldn't try, you know, throw, you know, basic XGBoost models at this and things like that. So we needed more an approach that was probably more used to low number of data and stuff like that. Okay, so if you work in Agile, you would see a definition of done. This is essentially what we worked with them to construct. This is essentially our definition of done. But the takeaway is that they really wanted a dynamic pricing. You know, they wanted to say, like, if COVID happens again, I want to know that my algorithm can, you know, adapt and learn new customer behavior, because as we've all seen, you know, customer behavior changed really drastically. If you look before COVID and after, we've seen some massive differences in customer behavior. So we want to be able to pick that up in real time. So our pricing, the pricing product that we give them has to be dynamic. It also has to control the stock levels. So we want to make sure we don't sell out too quickly of each one of these bands, but not too early. So the hypothesis of most of these sort of airlines is that if we can hold out the stock until the end, we can charge a little bit more. You know, that's kind of the hypothesis, is that when you're 5 days away from when the flight departs, customers want to spend more. You know, whether that's true or not is actually our RL agent will actually learn that. So yeah, so that's interesting. Okay, so just brief introduction to reinforcement learning. Hopefully it's at high level enough that everyone can sort of follow along, but essentially it's a sort of subcategory of machine learning. Most of you would have seen lots of games being played, AlphaGo, things like that. This is much more basic than AlphaGo. You essentially have an agent which interacts with this environment, very much like a feedback loop. It will perform an action. In this case, it sets a price. It will receive a reward. This is basically like how much money have you got and how many have you sold, how many are left, that sort of thing. So you apply punishments, don't just reward revenue. So anyone doing reinforcement learning, don't just set the reward as revenue. That's not good. You will reach very unethical behavior in the reinforcement learner. And what it aims to do is learn a strategy, or which called a policy in this case, to maximize reward over time. So that's what it does. I think it's much more useful to this picture here. I think a lot of you would have seen this picture before. But you have an agent. This is the thing that makes the decision. It says, what action should I take given the state of the environment I'm in? Your action in this case is setting a price, or 5 prices simultaneously in our case. You interact with the environment, so you wait for a day to see what customers do. You receive some reward. In our case, we'll talk about it a bit later, but it's, you know, basically revenue with a penalty term for the rate of which you're selling. So you don't want to just set maximize revenue. You also want to make sure customers are wanting to spend that, right? Like there's kind of a trade-off there. Obviously, you don't want to sell everything at 50 quid and sell 3 seats, right? And then you have this state. This is really fundamental. This is the thing that we as data scientists have to figure out, is how do we represent the environment? How do we encode it, essentially? And we'll talk about what we did. But the reward is quite simple. The business will tell you how they measure success. We will give our ethical instruction to them on how you constrain that reward. And the action is also governed by the business. What minimum price do you want to set? What maximum price do you want to set? And things like that. So actually, from our point of view, the state part is the part that we have to really focus on. A few bullet points from just a few learnings from us. This isn't our first RL project. So just a couple of pros and cons. RL is dynamic, massive pro. A lot of people right now, a lot of traders are looking for a dynamic environment. Great for new environments. Our particular client had the case where they were selling bags with seats, and they took away that. So now you just buy seats and bags separately. But it seems that now they have no idea how to price seats, or they don't know how to assign value to that. So it's great. We can run this in a new environment and take data in an efficient way. So RL is great for that sort of thing. And in general, depending on the RL method you use, there's only a couple of parameters to tune, which is also great. A couple of the cons is you can't say beforehand how well it's going to do. If they've always set £5 for our standard seats, for example, that could be the optimal. That could be where the maximum, performance is. But if we want to try £6, which they've never tried before, we might be able to infer a little bit about what £6 will do because we've tried £5, but we can't say for sure what it would do. So RL is a learning thing. It's like going out into the wild, trying things on real customers and learning from it. And a lot of clients will be a bit icky about that. So it's really down to how you explain what's going to happen to them and really set expectations, which we'll probably talk about in a minute. Yeah, difficult to explain. That's pretty much what I just said. And it's new to a lot of stakeholders. You say reinforcement learning and a couple of them get a bit scared. Some of them get excited, which is good, but a lot can get scared. But I'm going to pass over to Ben to talk about a little bit more detail on what we decided to do in the end.
So yeah, I'll just give you another very brief overview to Q-learning. So hopefully some of you are aware of what Q-learning is, but it is a technique within reinforcement learning. We selected this mainly due to its simplicity. So we had run RL projects with other clients previously, and we know that a lot of the time we recommend prices and the client says, yes, but why is this price suggested by the RL agent? So yeah, we put a lot of emphasis on keeping things simple and explainable. And we kind of think that it essentially automates the process that the traders are doing already. So essentially, Q-learning looks at every state and every action that you can perform and gives a value that represents how good is it to be in this state and take this action. An example of that could be that for this flight, so given where we are in the selling period, how many seats I've got left, what the ticket price is, how good is it to set these seat prices, and these Q values are basically just stored in a very big table. So a dimension for every state and every action, basically. So if you want to find out the optimal price to set, you just read off of the table, what state am I in? Let's take the maximum Q value and set that price. To update the Q values, we use this function at the bottom here. So this is just the Q value update function, but I think it's relatively intuitive. So on the left-hand side, you obviously have the Q value for that state and that action. And then parameter by parameter, you have the Q value that was there originally. So how good did I used to think this action was before I received this new bit of information, multiplied by a learning rate. So just how much of my value do I want to update, multiplied by the direct reward I've just received from taking this action. So if I've just sold some seats, that could be the revenue that I got from selling those seats, plus a gamma term, which I'll talk about, multiplied by the maximum Q value that from the state that I'm currently in as a result of the action that I just took. So you can think of that as how valuable is the state am I in now, which is useful if you think about the fact that the action you took previously got you to where you are now. So it might be the case that I sold no seats, but that means that I've got loads of seats still left to sell, and it's very valuable to have these seats left to sell, given where I am in the selling, in the kind of booking curve. And that gamma parameter just lets you prioritize that part of the update. So if you really want to pay a lot of attention to those future rewards, then you can set that gamma value high. The other thing that we haven't really mentioned up to this point is there's obviously in all reinforcement learning techniques, we explore some of the time and we exploit some other another percentage of the time. So every time we are setting prices, the agent has two options. We can either explore and set a random price, or we can exploit and set the current best price. And we control how often we explore by setting another parameter called epsilon. Cool, hopefully it's still with me. So how did we set up the model in this particular case? So as I said, we really tried to keep it as simple as possible because Q learning is just one big table. It's obviously very memory intensive. So tried to reduce that as much as possible. So not too many states. So we consider the time to departure. There is an idea that people are willing to spend more the closer you get to departure. Whether or not that is true, that's not so much for us to say. It's just the airline's perception. The ticket price we consider because it kind of makes sense that the higher the ticket price is, the more you might be willing to spend on the seat. And obviously the supply of the product. So consider how many of my seats do I have left. The reward that we've defined is a combination of revenue per ticket, which is really useful because those are the metrics that our stakeholders are already speaking in. Makes it very understandable for them when we're showing them results. And as Jordan was saying, we also consider conversion rate in this reward, which again I'll talk about in a second. And then the actions are quite straightforward, just a combination of 5 prices, so 3 premium bands and 2 standard bands. Action will either be to explore or exploit at every time step. So some of the project-specific challenges that we've come up against kind of all around the same kind of thing, is that our premium seating products are constrained. So bands 1 and 2, which if you remember are front seats of the plane and the extra legroom seats at the front, they nearly always sell out, and there aren't many of them. I think band 1 seats, sometimes there's only 6 of them per plane. So we've got a whole year to sell them. So when is the best time to sell them is something that kind of the focus of this project. It probably isn't optimal to sell these straight away. So we need the value of that state action pair to reflect the value of taking an action at the start, given that we have a whole year to sell them. So the solution here is to set that gamma value that I was just talking about very high. Similarly, there are some business constraints to consider along the same lines. So reputationally, it wouldn't be good for airlines to sell out of seating early on in the selling period, because you don't really want to be booking a flight 2 months out. If you're the kind of person who wants to spend a lot on a premium seat, you wouldn't want to find that they're unavailable because we sold them all a year ago. So we sort of thought about, can we additionally constrain the RL agent so that we can't learn that it's optimal to sell out early, even if it is. So yeah, we constrain the rate of sale using a penalty, which I will talk about now. So as I said, it might be optimal to sell the seats early, but it wouldn't be good reputationally. So to account for this, we've also built in a penalty system according to the rate of sale. So we looked at the historical rate of sale, and our hypothesis was, if this is the historical rate of sale, then the traders must be happy with this. So let's stick to somewhere within this region. So we look at, when we sell a seat, we look at what the percentage of tickets that we've sold for that flight is, and we try and stick around that percentage for that, for the percentage of seats available. So you don't want to have sold 20% of your tickets only, but already had all of one of your premium seat bands gone. So if that's the case, even if the revenue per seat, even if our reward for our agent is really high, we will penalize that because we know that the constraint of the rate of sale would not be okay from the stakeholder point of view.
Yeah, can I add, it's worth knowing that from a mathematical point of view, this basically means that we're not guaranteeing convergence anymore. We're not really letting it do whatever it wants, right? But when you're working with real life clients, you can't just let it go, try everything at once. You have to constrain it, whether it's from a business point of view or whether you consider an ethical point of view to some of these things. So you have to consider that with reinforcement learning. It will, because you randomly explore, that's the way that we explore. To guarantee that convergence, you have to randomly explore every possible state action pair. You have to constrain, in my opinion, you should constrain it in some way. I think from previous projects, it's definitely worth doing, or thinking about how you want to do it from an ethical point of view, especially, and from a business point of view.
Cool. And then, yeah, just quickly on results. So we've been testing this over, I think, start of October, I want to say, we started testing it. And yeah, we've seen a 10% improvement in revenue as a result. We're monitoring RL specific metrics to guide how we tune the model over this testing period. We know that even though there's only 2 or 3 parameters to tune, these are sometimes quite hard to tune, and there's no real rules, so you kind of have to do it by experimentation. So I think it's good practice, if anyone's going to run anything like this in future, to just record as much as you can as you're testing things live. So yeah, we're recording all of our states every day, and when we explore and when we exploit, so that we can really break down that performance. We're also monitoring when the explore prices that we've set become exploit, and using this to inform how our agent is learning, which has been very valuable. Currently, we're exploring most of the time because this is the first time we're able to offer prices. So if the airline is happy with the risk, then why wouldn't we want to do that? But yeah, we'll look to bring this down to about 10% of the time once it's clear that the model is performing how we want it to perform.
Yeah,
I think.
I think as well that reinforcement, the optimal price here isn't necessarily set a higher price. We found it will set higher prices sometimes and lower prices other times. We make sure that conversion rate of more like customer, or demand is still the same, so in general, actually our standard seats have gone down in price, I think, in general. I think some of the front row seats, really attract business people who aren't actually paying out of pocket to the company, and that in general wants to increase the price a bit. But we want to make sure we don't price people out. We're really monitoring that and being very careful on that sort of thing. Just want to say that because pricing projects can very much feel icky, but we are very cautious of what we're doing. Yeah.
Cool, thanks. Any questions? Yeah.
The terms explore and exploit, like that implies you're doing something like intervening in the system, pricing. What actually goes on there? Yeah.
Yeah. So the question for those online is, what is explore and exploit?
Yeah.
So I guess exploit is quite a emotional term, maybe. But it's really exploiting what we know about the system. So we know that some prices are better than others because we have measured that by training the RL agent. So when we exploit, we just choose the price that has historically performed the best according to the reward that we've defined. When we explore, we're literally just trying something else. So let's see how that price performs for a bit, because we know that there's a chance that it performs better than what we currently know is best.
Yeah. That captures the drift in environment change, customer behavior change, or price sensitivity change. If you explore some of the time, eventually you will capture that change. And the amount you explore and how much you weight your alpha, which is your learning rate, you can basically tune your alpha to how much you think things are changing in terms of customer behavior. So if like I'm touched with COVID, doesn't happen again. You would be like, something's changed, set alpha really high. We need to start learning about now what is happening now. So yeah, so that's the idea or the intuition behind it, I think.
Yeah.
External factors such as how many other flights you have that are flying to the same destination, or the weight, the balance, the weight balance in the plane. How do they impact your algorithm? Or where do they feed into your algorithm?
So I think the question was, how might external factors influence our algorithm? The honest answer is they could affect things. So we have tried to keep the states as simple as possible due to explainability and engineering challenges, I would say. There's every chance that there's a state that we haven't considered might start affecting things, but that's why we test. So we haven't really seen any. It looks like it's running well at the moment, but yeah.
One way to deal with that is at the beginning of the project, work with your client to actually draw a causal tag, like what is causing what is causing a customer to spend more money or less money, this external factor, really draw it and picture it. And that can help you sort of come up with those states. I think that would be how I would do this again, if I could do it again, rather than just saying these ones are roughly good, But I don't want to choose.
No, just someone, whoever asks first.
I think that's in the grey market.
Okay.
Sorry. Question about that gamma. Could you go back to the equation? So you mentioned that gamma is at a high, so that your frequency is also out. Is that? Yeah, can you explain that?
Yeah, the question for those online was, what is gamma and how does that stop us selling out? Really what we're doing here is we're setting up like really working on a Markov decision process. So we're constantly thinking about how our flight is evolving over time. When we are learning, we take an action. So we're in a state, we take an action, we end up in another state that's represented by that MDP.
S prime.
Which is S prime. Then we look at how valuable that next state is, so that we got into as a result of our action. And then we assign some of the value of that next state back to the state action pair from the previous step.
I think I know what So you don't actually have finite results. They encoded in your state, and you reach zero.
So you do, but because Q-learning assumes a Markov process, this S prime is the value of all future states up until the end of the
So
episode.
you have like the end where you know that tomorrow is the flight. So there will be
Yeah.
no.
Yeah, that's a terminate. That'll be when it terminates. So that final state doesn't get any extra value when you terminate. Yeah. So that'll be the end of this episode, essentially. Yeah, there's some good derivations of this online that are quite intuitive. Hopefully, it's easier to show you than say.
So I'm afraid that's our questions. That's okay. But thank
Yeah.
you very much for
No, thanks.
making the presentation. Might have enough time.
So we've had two, that's odd, isn't it? All right, so we've had two really cool applied data science talks. This is going to be very, very hand wavy as compared to those. So yeah, I'm Lawrence Knight. This talk is entitled World Models and Why We Need Them. So just a little bit about myself. So I lead a team of applied data scientists at a company called Vitality. It's a health and life insurance company. In terms of what I do on a day-to-day, me and the team do on a day-to-day basis, we do fraud modeling. We do a lot of process automation using large language models, trying to kind of streamline emails and socials going through the business. We have tons of people servicing those at the moment. We do things around sales and retention optimization. In my personal life, well, do some other things in my personal life, but aspects of my personal life is much more research focused. So one of the things I'm working on is replicating a poker AI called Pluribus for an MPhil in computer science I'm doing. That's kind of reinforcement learning based, pretty cool. And another thing I'm doing as well is trying to kind of research a potential topic for a PhD that's kind of at the fringes of AGI. And this is where this talk has come from. I've got 10 minutes. It's going to take more like 15. We're going to really rush through this stuff. So what we're going to try and cover is what is intelligence, quick definition. Where are we on the AGI journey? There's a lot of hype around this, and I think maybe the hype sometimes has gone a bit far. There's kind of hype cycles I'm sure we've all seen charts of. We'll ask the question, are large language models AGI? And we're going to talk about, this is world models, so we'll ask what are world models, and we'll talk a little bit about what you might need to learn one. So what's intelligence? So Oxford English Dictionary would say intelligence is the ability to acquire and apply knowledge. A definition of artificial general intelligence. So like typically this is defined in relation to human intelligence. So it might be something like an AI system that is at least as capable as a human at most tasks. Typically when we're talking about AGI, there's a distinction between like cognitive and physical intelligence. We're typically talking cognitive intelligence, but I mean, I think physical intelligence is an important part of what makes us intelligent. I've got down there as well. I mean, this is a very broad definition of intelligence. If you're working with this stuff, you're probably trying to think and define which of these sort of subcategories of intelligence you wanted your model to be good at. So where are we on the AGI journey? Helpfully, DeepMind have recently released a paper in November 2023 called Levels of AI. And they're trying to kind of say, okay, well, where are we in our AGI journey? They sort of down there on the left-hand side, you've got rating AI from no AI down to kind of superhuman levels. And then we're splitting it narrow AI on the one side and then general AI on the other. So what it turns out, I think probably most of us in this room are familiar with, is that we're really, really good at narrow AI and not so good at general. So things like AlphaFold, which is DeepMind protein folding algorithm at superhuman level. I mean, I would argue that whoever's authored this paper says that the likes of ChatGPT, Bard, Llama 2 are equal or somewhat better than an unskilled human. And presumably if they're saying general, then at a wide range of tasks. My experience is that that is not the case. So are large language models AGI? I mean, I probably just answered that question, or at least give my opinion on what the answer to that is. But if we were to consider the kind of definition of intelligence has two parts. It's around the acquisition of knowledge and the application of knowledge. So in terms of acquisition of knowledge for large language models, it does not come easily. To train one of the more recent GPT models, you're talking $50 million to $100 million. That's Sam Altman at a recent Forbes interview. A lot of that is just kind of banks and banks of GPUs running. In terms of kind of environmental costs of training these things, it's massive. Whilst humans run on watts of energy per day, you know, it's a completely different scale. In terms of the acquisition of new knowledge, these language models do not acquire new knowledge easily. It typically requires kind of bottom-up retraining, kind of the likes of GPT 3.5 was out of date by about 2 years up until recently, because they can't acquire new knowledge on a piecemeal basis, while humans do that very naturally. And I think we'd want that from artificially general intelligence systems. And then application of knowledge. They're wonderful at knowledge retrieval, but they're not so good at common sense. They're getting better in their kind of prompting techniques, which help, but really they're not good at common sense. And common sense is something will be like a bit of a theme of this talk. So why would it be that these large language models wouldn't be good at AGI? So if we look at the human brain, so the areas in the human brain associated with language and speech are Wernicke's area and Broca's area. They're highlighted here in this little chart. They're very, very small compared to the kind of overall size of the human brain. So there's a lot going on in an artificially intelligent, a generally intelligent brain other than language. So why would we suppose if we were to build a large language model, it would suddenly become generally intelligent? So, I mean, if I was to try and like characterize human intelligence versus large language model intelligence, human intelligence is a fundamental understanding of how the world works with a kind of language layer built on top of it. Large language models are just auto-regressive models. They're generating text based on historic co-occurrence of words. What are world models? So if we're saying, and a point on this was that sort of the reading I've done says there's no real amount of scaling of large language models which are going to suddenly turn them into AGI. That's just unlikely to happen. So if we're not on this path towards AGI with current systems, and large language models are probably the closest thing we have to it, along with perhaps some stuff we're doing with self-driving cars, what is it that they're missing? So I would contend, and others would too, that is a model of the world. So birds and mammals, both having a developed neocortex, learn world models. I think that's relatively well documented. The neocortex is basically a prediction machine. It's making predictions in every sensory modality all the time. And for a neocortex to be able to make predictions about the world, it needs to learn a model about the world. It needs to have something to make those predictions against. I thought this was relatively humorous. I mean, these are the kinds of machines that mistakes that machines are making. You've got two cows, one obscured by a shed or whatever that is. But our knowledge of the world would not allow us to make that kind of trivial mistake, whilst sort of these current artificial models are doing that quite regularly. So just a bit more about how an artificially general intelligent system, or humans in fact, learn world models. Basically, our brains would plan an action, very much like kind of machine learning models work. You plan an action, your brain then predicts the change that action will have on the environment. When you perturb the environment, you execute that action, you observe the sensory response that comes back, and then you evaluate that sensory response and update your model if you find it to be inaccurate. And that's broadly what we're doing. Again, this notion of common sense. So kind of common sense can be thought of basically of having a robust world model. And I think we kind of, you can see that in humans, I think. So what kind of things would we want our world models to learn? What do kind of young children? So if we were building an AGI system, what kind of things would it need to learn to be able to reason about the world that we live in? 2-year-olds learn this stuff, without trying. The world is three-dimensional. Every source of light, sound, and touch in the world has a distance from us. Something about kind of a notion of objecthood. The fact objects can include more distant ones. Objects can be assigned into broad categories. So, I mean, you can kind of see these are just kind of common sense about the world, and there's something about how do we kind of instill this into large language, or artificial systems, basically. So what do you need to learn a world model? There aren't going to be any answers here. I don't think anyone has the answers, but it's interesting that people are just starting to kind of posit some ideas. So an appropriate architecture and learning algorithm is going to be really important. Sensors through which the world can be perceived are going to be important. A body through which the system can interact with the world. And all of those would be redundant if you didn't have a drive and a motivation to actually go out and actively explore the world that it's in. So, I mean, just sort of going through those one by one, an appropriate learning architecture. So the human brain's evolved over millions of years to get where it is. A chap, Jan LeCun, suggests that replicating a structure with a similar functionality is going to be the single greatest challenge to AI, AGI. A system capable of learning a world model is likely to have multiple modules working together that kind of that mirror the various functions in the brain. And what we'll just talk about a little bit now is a paper by Jan LeCun, a position paper. He's Meta's chief AI scientist and the father of convolutional neural nets. This was published quite recently, back end of 2022, called Path Towards Autonomous Machine Intelligence. It's long, but it's pretty interesting. So some of the things I mean, I'm not going to go into details here. It's a 78-page paper, but you've got a world model front and center of what he's saying you need. I mean, he's proposed architectures for all of this, which are learnable by, well, all of it, a good proportion of it that are trainable by gradient-based methods. So you've got a world model. Perception is like absolutely vital for this. You need to be able to perceive the world. You need to be able to turn those perceptions into kind of representations of the world. And you need to do that at multiple levels. And those representations need to, in effect, denoise what you're perceiving or what the system is perceiving. You need a cost function, so that in effect instills these motivations into the system. You need an actor to kind of plan or suggest actions that the system could take, and that the world model can then evaluate. So again, he's suggested some specific things around this, but just to give you a flavour. Another person who's thinking about this stuff is a chap called Jeff Hawkins. He published a book in 2022 called 1,000 Brains, A New Theory of Intelligence. And what he sort of says is the neocortex learns many complete models of objects and concepts, and that these models work together to create your perception of the world. They're a bit, just on that chart, there's a classical view. So if you were to think about kind of a convolutional neural net, how it might recognize an object, you get an input, and then it kind of learns in the lower layers the kind of simple features, and then more complex until it can make a classification. His theory is that you just learn lots and lots of representations or models of objects in many parts of the brain, specific to the sensory modality. So the skin will have its own understanding of what a coffee cup is. In this instance, the retina will have its own understanding of what a coffee cup is, and then there's a whole voting process when you're perceiving an object. And then he talks about this thing called reference frame. So any object that's learned by the model is anchored to a reference frame, and that's quite a kind of a unique take on things. Just a couple of these things that come out of his series. So he says the neocortex is completely homogeneous in structure. So if you kind of looked at a neocortex under the microscope, you can't say, oh, this is like where you hear, this is where you see things. It is a homogeneous structure. It's the same all the way through. So there are specialist reasons for seeing, touching, language, high-level thought, but they're not specialist in the sense they have a different inherent structure. He calls the fundamental structure of the neocortex, or the unit of intelligence, a cortical column. Brain's made up of 150,000 cortical columns. They implement a fundamental algorithm that's responsible for all aspects of your perception and intelligence. The thing that's kind of interesting about that is he's saying is, well, if you can just learn how that one cortical column works, then you can just scale it, basically. And unfortunately, they haven't published around specific things that they're doing, but in his book, he sort of talks about having, built represented these things in code and experimenting with them. So the brain arranges all knowledge using reference frames. He talks a lot about like motion and movement. This is how we're learning the world, through motion, movement, perturbing the world, check it against our world model. And his thinking is that, thought is also a kind of a process of movement, if you will, or abstract movement through positions and reference frames in your mind or in your brain. So getting to the end, so we talked about what do we talk about? We talked about sort of like an appropriate learning architecture. So a couple of other things you need sensors. So to be able to kind of experience the world you're in, you're going to need sensors to perceive it through. The sensors that you bestow upon a system will fundamentally impact or dictate the world model that system will learn. Visible light gets its name. Our eyes are configured to be able to perceive visible light. Visible light is a very small proportion of the electromagnetic spectrum. It'd be very easy to imagine that artificial systems would have different types of sensors, and they would perceive the world in quite a different way. And embodiment's going to be super important. We've talked about, I've mentioned it before, animals learn world models by interacting with the physical world, a process called sensory motor learning. I think probably if you're going to learn, if artificial systems are going to learn about our world, then they're probably going to need bodies through which to interact with it. I'm not going to say anything on self-driving cars, but it's probably the area that's most using this kind of technology at the moment. And I think having difficulty with it. I think people like Uber and whatnot are kind of pulling out of the race. And I think that just goes to show like how difficult a thing it is to learn a world model. This is not straightforward stuff. So key takeaways: current AI systems seem to lack what we would call common sense. Common sense in animals can be attributed to having robust world models. Animals learn world models through interacting with and perceiving their environment. The neocortex is a prediction machine that learns and encodes a world model. World models are likely to be critical to the success of AGI, and it's likely, in my opinion, that artificial systems will need to be embodied to learn world models. That's it.
Excellent. Okay. Hi there, everyone. My name is Daniel DeBurgo. I'm a consultant here at Daemon. And last year, I started an initiative. This initiative was all about properly accepting and making the best use of generative AI that we can. Here at Daemon, we're really passionate, and this project was all about finding those key insights into how we can maximize and best use generative AI. And this project produced a lovely bot that everyone in the company can make use of for producing passionate blog posts. But the main points are about those key insights as to how we prompt engineer and make the best use of these generative AI technologies, such as ChatGPT, that we can. And those insights are what I wish to impart over the following slides. So, what is ChatGPT? For those who aren't familiar with ChatGPT, it is an AI-powered text generator. Lots of people are familiar with its capabilities and power. It's had an explosion in popularity over recent times. It's been unprecedented. But are those capabilities being used to their best possible potential? Over the following presentation, I wish to impart how I view ChatGPT in terms of a philosophy and a methodology of making the best use of this technology. I really want to make sure that I hammer home that ChatGPT can be used as a problem-solving solution to traditional areas of programming that haven't been solvable by traditional areas of programming, truly using AI for its potential in solving human-focused problems. So AI has always been used to solve problems that traditional code cannot. And in every single case, we have to be clear about what we expect from the AI tool we create. If we're making a robot to give hugs, do not expect it to save a penalty all that well. So why do we view ChatGPT as a magic bullet that can solve any problem that we give it? If we have a problem in our mind and we have a problem in our mind that we want to solve and we want to find the best solution for that problem, we need to set out our own expectations. We need a measure of success, and that measure of success is going to be completely different for every problem that we're trying to solve with ChatGPT. We need to understand that ChatGPT works under the assumption that the input you give it will lead to the output that you've been searching for. And I think everyone in this room who has used ChatGPT will know that's not always the case. Whatever we give it isn't necessarily going to give us what we've been searching for. And is that the fault of ChatGPT? Not all the time. That can be our fault. We might not have given it the correct prompt for what we wanted to get out. So how do we maximize that? How do we change our prompt to get what we actually wanted from that prompt? So it's all about understanding the problem you want to solve and measuring the success of the ChatGPT proposed solution. It's all about how we think and view the input that we're giving it and the output we're getting back. So let's take a look at applying this method. So to apply this philosophy to ChatGPT, we're going to start where every programmer starts the solution to every problem that they ever solve. Divide and conquer. we're going to take one big problem that we want to solve, and we want ChatGPT to solve in this case, and divide it into lots of different sub-problems. For those who aren't familiar, the classic example of divide and conquer would be making a cup of tea. We can split this into boiling the water, putting the water in the cup, adding the tea bag, the milk, etc. And obviously there can be a lot of controversy as to which order you perform those steps. In our case, we really need to think about what we care about most within our solution when we're defining our sub-problems. For example, when we're solving a problem where we want ChatGPT to perform the role of the interviewer, do we care more about the kind of questions we want ChatGPT to ask us, or do we care more about the feedback that we want to give it? These are separate problems, and we need to be aware of that. We could break these problems down even further. For example, the difficulty rating of each question that we wanted to ask, or tailor our feedback to specifically what the interviewer that we're going to be interviewing with in real life is looking for. So the prompt, as you can imagine, with all of these little sub-problems, can get very, very large. So we start small. We start with lots and lots of small problems that we want to solve, and we take each one on individually. We write a small prompt, but we don't hit enter. We write our own response to that prompt ourselves as a human, which will set our expectations of what we want ChatGPT to produce based on that prompt. Then we hit generate, and we're going to continue modifying that prompt until what we get out of ChatGPT matches those expectations that we've already defined. And once we've got something that matches our expectations, we can improve. We now have a new prompt, something that we've engineered ourselves to meet our expectations. We can now write a new output, which will be a better solution to the better prompt that we've just generated. Each time we do this, we're getting more and more specific, and the prompt grows in complexity, but so does the capabilities of the solution to the small problem that we have just solved with ChatGPT. We then follow this method again. We press generate, we modify the prompt until we get something resembling what we have written. This could go on forever, increasing in complexity. The key part of this method is finding the right level of that complexity. You can repeat the method until your output from ChatGPT does not improve. In ML terms, we found a local maxima, and we can move on to the next of our sub-problems. Once all of our little problems are solved, we have lots and lots of large prompts. We can then smush all of these prompts together into one big prompt, and this will solve the general problem that we set out to when we started. So let's look at this in a case study. Blog automation was all about making it easier for people to write passionate blog posts here at Daemon. We want to showcase our passion as much as we can, but there's several hurdles involved in writing blog posts, and these are the problems that we set out to solve when starting this project. If we'd taken the naive approach and just asked ChatGPT, here's a blog post topic that I want to generate, please give me a blog post, it would just give us a standard blurb of repeated information that is available elsewhere on the internet and does not showcase the person's passion for that topic area. Passion can only come from one person's own voice. So let's introduce the problems that we're actually solving, the sub-problems that we defined when applying this method. Blank page syndrome. This is where you have an idea, but you're stuck where to start. We've all been there looking at a blank text editor with so much potential, but absolutely no direction. We wanted to be able to give our bot a topic and return a structure, which is a great starting point to solving the age-old problem. Writer's block, however, is a much broader issue than just blank page syndrome. So we wanted to solve that as well. If you're halfway through writing a blog post and you've caught a bit of writer's block, we wanted to be able to take what we've already written and offer a direction to that person, finish off what they've already started in a similar style. It's a great way to make sure you get over the hurdles where you have something, but you're not sure where to go next. And the final issue that we attempted to solve with this bot is grammar. If you're unsure of structure or grammar, we wanted an endpoint to fix those mistakes. It could also restructure anything that it deems necessary. It may reorder or rewrite some sentences, but most importantly, it would make sure your finished post is polished and structurally sound. Each of these problems needed its own query that needed to be optimized and changed and made sure that we would solve those problems. So that's what we did. And we should be able to see a demo. How do I press play on this? In this view, I don't think I can. Can I do it on here? There we are. There we go. Excellent. So here it is. Here is the blog automation tool as it's finished. It's a Slack bot. We can type /blog, and there are 3 endpoints: generate, complete, and edit. Those endpoints solve each of the problems that I just mentioned. At the moment, I'm entering a prompt for a blog title. I'm stuck with blank page syndrome. I have a really cool blog title that I want to write about. In this case, it's Asimov implications on tech. And I'm going to press submit. What's going to happen? The blog, well, right at the bottom there, it sent me a message saying your blog post has been received, and we have to wait for it to be processed. In the background right now, ChatGPT is generating a nice structure for us for this blog post, which will give me, as the writer of this blog post, a really great starting point as to where I should take this blog post and be able to put my own voice into that structure. So as you can see, it returned nice beefy blog posts with 4 sections. You can take a look at these in your own time. I'll make it available after the presentation. I don't want to get boiled down too much into the detail there. But we also have a token balance, which allows us to measure the costs and things like that. But that's a brief demo of how that's all working. So a quick shout out to the Demonites that made this blog bot. We've got Charlie, myself, Jay, Joe, Jamari, and Nahin, who also happens to be in the room. So further applications of the methodology that I've outlined today. This method could be applied to a wide variety of human-centered problems. Some examples that I've put some clip art on the slide for there would be recipe ideas tailored to specific needs, bookkeeping help across every step of filing a tax return, events planning management, and information storage, just to name a few. During this presentation, has anyone here considered using this method on their own use case? Please raise your hand. Excellent, we do have some hands. I've done something good today. I'm very happy to get us thinking like ChatGPT, human-centered engineers, and that is my work for today done. Thank you very much. Do we have any time for questions? 2 questions, off we go. Go for it. Sorry, could you repeat that?
The ChatGPT just released out some agents or some kind of new technology that you can build your own.
Yes.
Can you just explain something like what do they do and all?
So we're not using that technology in this project. Obviously, that technology is now available. You can build your own agents. You change the system prompt essentially in order to do that. We haven't changed the system prompt. We're using it out of the box. But if you wanted to engineer that, I'm sure this methodology could apply to the system prompt as well as any other prompts that you want to generate. Cool. One more question?
Yeah. Well, it's kind of related to what he was saying, but so a lot of the stuff you're doing there, it seems quite similar to like GPT research, like the breaking down into tasks and then having like a deterministic parallel problem.
Yeah.
But with what he just said, it's actually not the agents. I think Bedrock uses agents, but OpenAI it's called assistants. And it's basically like a chain of thought around retrieval augmented generation.
Okay.
And also the ability to call functions. So it kind of uses step-by-step things. Well, not reasoning, but
AI reasoning.
To basically decide what to do, whether to call functions, whether to call the files that it's generated. And the advantage to that, from my point of view, when it comes to what you're doing, is the fact that the latency of the content that you're sending over to the actual API gets reduced because you're now storing a lot of your files over on the API side where you're using their retrieval object.
The sort of prompt engineering is done on their side.
Well, some of the prompt engineering is on their side, and then you can do the rest of the prompt engineering
on yours.
Kind of just to treat it between the two.
Okay, yeah, I see that synergy, and I very much welcome it. I'm not sure there was so much a question there, but
my question was, it was the same question, whether or not you had actually tried using that, because I think you had to cut down some of the stuff you.
Personally, I haven't tried it, but I'm more than happy to. It seems like a very great idea. I'll have to research it in my own time. This project was started at the start of this year, so I'm not sure that technology was available at that point. Right, so definitely not. So I'll have to research it in my own time, and thank you for pointing that out. I definitely will. But yeah, at the moment, currently not used in the method. Cool. If you have any more questions about the method or you wish to have any help with applying it, then there is my email address. You're more than welcome to reach out to me. Cool. Thank you very much.
So I'd first just like to say a big thank you to all our speakers this evening and for everybody that's listened so carefully. It has been an incredible evening, but a big thank you to Damien, Jenny, Ben, Jordan, Lawrence, and Dan. Another round of applause for them all. So our next one, we're gonna take a break in January, so that we can obviously all recover from Christmas and have a bit more time to plan ahead for February when we'll be back. So please keep an eye out on the Meetup webpage, and the next event will go live towards the end of January on there. And if you would like to be a speaker at one of our meetups, then please feel free to submit a talk. This is the QR code, or come and speak to me at the end. That's it from us. Thank you.